Chapter 8 deals with matrices, okay, for these systems of equations. Now, matrix in general looks like what? Yeah, basically it's just a big array of numbers. It's a big rectangular array of numbers. Doesn't necessarily have to be square. Now, positioning-wise, they describe the positions by saying A. So if this is matrix, they'll usually use capital A equals this, and then relative position, they'll say A and then I, J. I describes which row you're in. So first row, second row, third row. J describes the column. So if I say A2, 3, it means you go down to the second row and over to the third column. Not A23, nope. So then, M by N also describes what's called the order of the matrix, or I honestly think of it as the dimensions of the matrix. The book will refer to it as the order. So M is the number of rows, N is the number of columns. Okay. You also have what's called a main diagonal. The main diagonal will be the ones where you're row 1, column 1, row 2, column 2, 3, 3, 4, 4, 5, 5, so on and so forth. Okay. Just some of the terminology stuff. Now, looking at these matrices, what's the order of the first matrix there? In other words, what's its dimensions? 1 by 1. So you just write it like that. For B? 3 by 1. For C? 3 by 3. For D? 2 by 4. So then, a couple other terminology-wise, you have what's called a row matrix and a column matrix. Which one up there is a column matrix? B. B. Literally, it's just nothing but a single column. Row is nothing but a single row. Then you also have a square matrix, which would be C. You can make an argument for A. That's usually just, what does they refer to that as? I want to say constant matrix. I don't know if this book actually calls it anything. A single number by itself. Yeah, we talked about all that. Down here. Now, when you have a system of equations, you can actually turn that into a matrix, a couple different versions of the matrix. You can have what's called an augmented matrix. This is the one I probably use the most often, where it has all your coefficients on one side, and then what each equation is equal to on the other side of this dotted line. I usually don't even bother putting the dotted line. Coefficient matrix is a square matrix. Well, it doesn't have to be a square matrix. It's just a matrix made up of all the coefficients. Now, there's a technique for doing this on your calculator using the coefficient matrix and then what other matrix? How would you solve this using your calculator? Anybody remember how?
Like the inverse of
the inverse of what?
the
Inverse of the coefficient matrix, and then do what with it?
multiply times the result.
Times this constant matrix over here. You can actually make a column matrix out of these constants. Take the inverse of this matrix times that. That will solve it. But remember, no calculator on the quiz. So we need a different technique for it. Okay? Now first off, if I wanted to create an augmented matrix for this, and this is what we're going to work with, is that augmented matrix. Augmented matrix, if I could talk. What would the augmented matrix for this system look like? So 1, 1, 1, 2. 2, negative 1, 3, negative 1. Anybody? Negative 1, 4. Honestly, if you want to put the dotted lines, do it. If you don't, don't. Part of the homework will literally be just making those matrices. Okay? What we do with them after the fact is actually something we've already done before. We've done it with versions of these equations and use some basic manipulations to try to get them into a simpler form. Well, these are what are called elementary row operations when we're talking about a matrix. But we've done these before. Once you have that augmented matrix, you can always swap two rows of the matrix. Well, that's the same thing as switching the order of the equations, right? You can multiply a row by a non-zero constant, and you can add a multiple of a row to another row. We've done all these before. It's just, instead of writing the x, y, and all the pluses and minus signs all the time, you can just take that matrix and work with that. Okay? So, if it asks you to interchange rows 1 and 3, well, what would that end up looking like? So that would be your matrix. What about for B? What would remain the same for B? Hmm?
0. No, the 1 and 3 would stay the same.
Yeah, row 1 and row 3 would not change because it's saying multiply row 2 by negative half. So row 1 and row 3 remain the same. What about row 2? What would that turn into? Is there any shorthand way I could indicate what I'm doing to row 2?
Outside the matrix, on the inside, it's just right in. I don't know.
Can you have like a row? It's either a row matrix or a column matrix. It's like 1, negative 1 half.
Oh, you're trying to think of a way you could multiply something by that? Yeah, there's ways you could do that. I'm actually thinking of shorthand, like just a quick way to write to explain what you did. You're making that way more complicated, but yes, there is a version of that you could do. There you go. Negative half row 2, replace row 2. That's all I was looking for. You're not wrong. There is a method where you could actually take a very complicated matrix and multiply it times that matrix, but not worth the effort right now. What would that shorthand be for C then? Negative 3 row 1 plus R2. And which row am I replacing? R2. So again, top row is going to remain the same. Bottom row remains the same. What does the middle row turn into? So negative 1. You're going to take negative 3 times 1 is give you negative 3 plus 2. Negative 8. Negative 3 times 0 is just 0 plus negative 8. Negative 9 plus 4 is negative 5. Yep. Negative 18 plus nothing is negative 18. Okay, so there's going to be a lot of multiplication going on because often you're going to be given this and just asked to solve it. Well, but I want to solve it with matrices and without a calculator. So what would I need to do first to solve it with a matrix? Yeah, turn it into a matrix, that augmented matrix. So top row, middle row, bottom row. Okay. Now, thinking back to the equation version of this, if I was just looking at this, what would be my goal for the next step? What would I want to try to do? Yeah, get rid of both x's. In other words, get the coefficient on those x's to turn into what? 0. So what I want to do up here is turn the 2 and the 3 into zeros. What could I do to turn that 2 into a 0?
Multiply it by 0.
But the problem is that would change everything to a 0. That would change the 2, but I want to change not everything into the same number.
You should have been more specific.
Yep, negative 2R1 added to row 2. One thing though, the top row, if it didn't have a leading coefficient of 1, first thing I'd want to do is turn it into a 1, right? So there could be one step before this, but top row is going to remain the same all the way down. This middle row, well, what's it going to give me? Well, obviously first it'll give me 0 because we picked the number for that. Yep, so negative 6 plus 7 is 1. Negative 8 plus 5 is negative 3. And negative 14 plus 10 is negative 4. Now, I like being lazy, so I'm going to also change the 3 to a 0 as well. Do it in one step. What would I actually need to do in order to do that? Negative 3R1 plus R3. So again, I'm going to get 0 here. What am I going to get for 1? Negative 9 plus 10. Next.
Negative 8.
Negative 8. Negative 3 times 4 is going to be negative 12, plus 4 is negative 8, and 6. Negative 21 plus 27 gives me 6. Now, what do I need to do next? Or what do I want to try to do? Yeah, the y coefficient, that second number, I want to turn that into a 0. Now, again, though, since this already has a leading coefficient of 1 there, I don't need to do anything with the second row. So the second row and the first row are going to just be carbon copies of what they already were. The third row, then, what am I going to do with? Multiply what by negative 1?
Second row.
Second row, yep. Multiply row 2 by negative 1. So negative row 2 plus row 3.
So 0, 0.
So you got negative of negative 3 plus negative 8?
So negative 5.
Negative 5. You have negative of negative 4 plus 6? 10. Okay. Now at this point I can honestly go back to equations, but I'm going to go one more step just so I get a nice leading coefficient of 1 on each thing. What do I do to that bottom row to get a leading coefficient of 1?
Multiply by negative. Well, divide by negative 5.
But I'm not allowed to divide, so negative 1/5, row 3, yep. And replace row 3. So 1, 3, 4, 7, 0, 1, negative 3, negative 4, and 0, 0, 1, and negative 2. So from there, I'm going to go back into the equation form of this thing. So I have x plus 3y plus 4z is equal to 7. Y minus 3z is equal to negative 4. And z is equal to negative 2. So what am I going to get for y? Because I'm going to plug negative 2 in for z, right? So that'll give me y plus 6. Negative 10. Then I'm going to take both those and plug them back into the top, giving me x minus 30 and minus 8 is 7. So x is what?
45.
45. So my answer is the order triple. 45, negative 10, negative 2. Now, some of the problems we'll just flat out ask you to, well, actually talk about that in a second. If they're just asking you to solve the system, you would need to get it down to that solution to the system, those three things. Okay? Questions on that one? All right. Now, these elementary row operations, that manipulation we just did, will also allow you to get to the matrix into two different forms, potentially. Okay? Sometimes they'll just ask you to, instead of solving the thing all the way out, they'll just ask you to get it to what's called a row echelon form or reduced row echelon form. Now, row echelon form means any row you have that's nothing but zeros is at the very bottom. Okay? So if everything cancels off of a row, it goes to the bottom. For each row that's not just a bunch of zeros, the first non-zero entry that you get to is a 1. Well, that just means leading coefficient of 1. Leading 1, they call it. And then any two successive rows, so any two consecutive rows, the leading one in the row above is further to the left than the one below. Well, that's why I actually did this and got the equation so it had a leading 1, right? There's no rows of zeros, so I don't need to worry about that. And you have this kind of stair step going down on that diagonal of the ones. So this is what's called that row echelon form. Okay? Reduced echelon form goes one step further with it. It makes it so for every column that has a leading 1, there's nothing but zeros above it as well as below it. Now, going back to this one, this is only to row echelon form. It has leading 1s in all rows, and there's zeros below them. What it doesn't have is zeros above them as well. What can I do to this second one, or to actually thinking of the third equation, to make it so there's there's a 0 directly above that 1. How could I manipulate that negative 3 and turn it into a 0? Any ideas? What was that, Jordan? 3 row 3 plus row 2, yeah. Because if I take 3 times row 3, that's going to give me 3 and negative 6. If I add that to this row, 0 times 3 is just going to be adding 0, so this first 2 won't change. That'll become 1, 0, 1, 0, and negative 10. Well, that's just y equals negative 10. If I were to take that and go up here, because I need that 4 to be a 0 as well, I would just take it times negative 4 and add it. How would I turn that 3 into a 0 here? Yeah, take the second row after you've made the change, because otherwise this negative 3 will get in the way. So you kind of work your way down, eliminating as you go along the left side, and then work your way back up once you get that bottom row down to 1 equals a number. But if you do that, so you'd have 1, 0, 0, 45, 0, 1, 0, negative 10, and 0, 0, 1, negative 2. So that literally just hands you x, y, z. That's what reduced row echelon form is. Okay? So honestly, it ends up adding usually 2 more steps. But if you look at what we did,
It's about the same as what we did.
it's about the same amount of work. Because if you just added 2 more steps here, you're using row 3 to manipulate rows 1 and 2, and then use row 2 to finish off row 1. Well, it's a little bit more work than that, but it's a little bit more writing. It's not really that much more work. Okay. So, looking at these matrices, which form is that first one in? Is that row echelon form, reduced row echelon form, or neither? Why?
0 is the bottom and then the
0 is at the bottom. You have leading ones. Why is it not reduced row?
because it's not just 1 equals a number. It has other coefficients. in that.
Well, but that wasn't the rule.
It's not zeros above and below.
There's not zeros above and below the leading ones?
There is a.
There's not a 0 above the first lead.
11 is not a 0.
There's zeros above and below the leading ones. This is reduced row echelon form. This one throws you off a little bit because of the 11 and the negative 2, honestly.
That does.
But it doesn't say it must have nothing but ones in the coefficient matrix. It says you must have zeros above and below the leading ones. Well, leading ones zeros, leading ones zeros. This is reduced row echelon form.
And the other one was neither because
The other one's neither because the zeros aren't at the bottom. If I swap these 2 rows, then would it be reduced row or just regular row echelon form?
Row.
Yeah, because the 3 and the 1 would be in the same column. What about C?
What about it?
Just
Row.
Just row, because you have zeros at the bottom, leading ones, but you don't have zeros above. So this is just row echelon form. For D?
same. The row.
Row echelon form?
Yeah.
You notice anything weird about it though?
There's a 1 on the. Wait.
It
is that
skips
everything?
It skips a y equation, yeah, which is possible. That could happen. What's the thing that makes this system of equations not work? 0 equals 1. You get a false statement for the last. Now, it's still row echelon form, but the systems of equations would be what for a solution? No solution. What about for E?
Neither.
Neither, because of the 3, there's no leading 1 in the second row. And for F?
Row.
Row echelon form. Questions on any of it?
It's going to be on the test.
Oh, yeah. We'll stop there for today. We do have more to do tomorrow for section 1. Because we need to get into we've done Gaussian elimination, we need to get into Gauss-Jordan elimination.